We saw that for one PMF, the variance of x is the expected value of the conditional variance plus the variance of the conditional expectation. And since one piece of evidence is enough to give a wannabe fascist ultimate power that turns a democracy into a dictatorship, this one bit of evidence means that this must be true for all PMFs and PDFs, both discrete and continuous. But unlike living in a free society, math is important. So let's see why this happens. So first, the expected value of the variance. Remember, the variance is the expected value of the square minus the square of the expected value. And since expected value is linear, we can break that apart. But the expected value of a conditional expectation is just the expected value of the unconditioned variable. Also, the variance of the conditional expectation, well again, that's the expected value of the square minus the square of the expected value. And again, here we have the expected value of a conditional expectation, which is just the expected value of the unconditioned variable. So when we add the expected value of the conditional variance and the variance of the conditional expectation, there's a term, the expected value of the square of the conditional expectation, that will cancel out, leaving us with the expected value of x squared minus the square of the expected value, which is just the variance. And this gives us what's known as the Law of Total Variance. Let x and y be random variables. Then the variance of x is the expected value of the conditional variance plus the variance of the conditional expectation. So for example, let's suppose the customers of an insurance product are categorized as high or low risk. High-risk customers have a 30% probability of a $1,000 payoff, and low-risk customers have a 5% probability of a $1,000 payoff. If 10% of the customers are high risk and the remainder are low risk, let's find the variance of the payoffs. So let's do this without the law of total variance first. So let's construct a tree diagram conditioned on whether a customer is high risk or not. So 10% are high risk, 90% are not. And of the high risk customers, 30% require a payoff, 70% do not. And of the low risk, 1% have a payoff, 99% do not. And so we can extend to find our probabilities. The payoff occurs only if a high-risk customer requires a payoff, and that has probability 0.03, and a low-risk customer requires a payoff, which has probability 0.009. And so the probability of a payoff is, and so the expected value will be, meanwhile, the expected value of the square is, and so the variance will be, so let's solve it again, but this time we'll use the law of total variance. We need the variance of the conditional expectation and the expected value of the conditional variance. So we're conditioning on whether a customer is high or low risk. So our expected value of the payoff given that the customer is high risk is, and the expected value given that the customer is low risk will be, so the expected value of the conditional expectation. Now, while we know this should be the expected value of x, remember we've only found that by computing it in the earlier case. So let's pretend we haven't done that work, but we can calculate it directly because we know the payoffs and their probabilities. And likewise, the expected value of the square of that conditional expectation. And so our variance will be, meanwhile, the variance of our payoff given that y is high risk, So for that, we need the expected value of our square and of our payoff given that y is high risk, and that will be and note here we're using the 0.3 probability because we know we're on this particular branch. And that tells us the variance. Likewise, we need the expected value of the square and the payoff given that y is low risk. So again, we use this 0.01 probability because we know we're on this branch. And so our variance of x given that y is low risk will be. So we can compute the expected value of the variance. Remember, there's a 10% chance that we're high risk and a 90% probability that we're low risk. So our expected value will be. So pulling in our earlier value of the variance of the expected value, and consequently, the law of total variance says that our total variance will be, which is the same as we got before.